This is lesson 2.8 on essential graphs. Now this lesson is going to be a little bit different than our previous lessons. There's really not much theory, not much need for examples for this lesson. Basically, there are 8 graphs that I want you to be able to recognize by sight. So just given the equation, I'd like for you to be able to sketch the graph, and vice versa. If you see the graph, be able to tell me what equation it is. Now for the drills, it's going to be more that latter situation. I'm going to give you the graph and ask you to tell me what is the equation for this graph. Now in our next section, you're going to need to be able to use the other direction. Once you recognize the equation, be able to quickly sketch the graph. Now remember that using graphs is a common way to represent relations. Remember, relations is just a collection of ordered pairs, and so each ordered pair corresponds to an ordered pair in the plane, or a point in the plane. Remember that the graphs of functions satisfy the vertical line test, so any vertical line that you draw through that graph is only going to cross it at most once. Now, we are only going to look at graphs of certain functions here. Later on we may talk about corresponding graphs of relations, but for our purposes right now it's going to be better just to kind of hone our attention on some specific functions. So once again, what follows are 8 graphs that you really just need to be able to identify both ways. If you see the equation, have in your mind what the graph looks like. If you see the graph, be able to recognize, oh, that's the shape of blank. Alright, first off, y equals x, that's the basic form of our simple ordinary line. So just any sort of diagonal line, that's going to be some variation on the basic equation y equals x. Next is our parabola. So we've seen parabolas before. This is going to be some variation on our basic graph y equals x squared. In the next chapter, we're going to be working with these guys just a little bit more. But for right now, I want us to recognize that parabolas and quadratic functions go hand in hand. They're the same thing. Our cubic graphs, y equals x cubed, kind of this weird, curvy, snaky looking thing. A little bit weird, a little bit awkward looking, but hopefully this is something that we have seen before. So we need to know the graph y equals x cubed. Into our radicals, y equals square root of x. You may notice that this is half of a horizontal parabola. It's the upper half of the parabola opening along the positive x-axis, but we only see the upper half because square root of x is only going to be positive. So y equals square root of x is going to be just the upper half of parabola. Y equals the cube root of x. It's basically just our y equals x cubed graph, rotated, well, not rotated 90 degrees, but technically we're doing something a little bit different than just rotating. We'll actually talk about that, not next chapter, but the chapter after that. So this is y equals x, y equals the cube root of x. Y equals the square root of r squared minus x squared. Now that looks a little scary, but if we square both sides, move the x squared over, notice that this is just our equation for a circle, x squared plus y squared equals r squared, solved for our y. So if we take that equation and solve for y, that will give us the graph of a function. Remember, circles are not functions. They fail the vertical line test. But a semicircle, the upper or lower semicircle, those are functions. So in this case, I believe we have chosen r to be 3, but r can be whatever radius we need it to be. So our semicircle graph, this is our absolute value graph. It's kind of an interesting one. It's one of the only ones that we're going to see where we kind of have a corner. Might not seem like a big deal, but once you get to calculus, you'll see that this is actually winds up being an interesting example. So absolute value of x, remember absolute value makes negative numbers positive and positive numbers just positive, so they don't do anything to them. And this last one's a little odd looking. This is what we call the floor function. Now this is the most bizarre of these. For this particular function, I am only going to ask you to, given the graph, just recognize what the equation is. I will not give you the equation and ask you to sketch it. This is what we call a discontinuous graph. Notice that the graph kind of hops around a little bit. The way this graph works is it's going to round down to the biggest integer that's less than or equal to whatever value of x is. So for example, if x is 2.6, then our y value is going to be 2. If x is negative 1.3, then it's going to round down to negative 2. If x is just an integer already, say 5, then it just leaves it. It doesn't round anything. So this is, again, our floor function. We round down to it seems weird, it's the biggest integer less than x. We're just rounding down. That's all that means, though. So this is weird, a little bit unusual, but it winds up being a nice example, again, later on in calculus especially. So I'll only ask you to recognize the graph. If I give you the graph, I want you to tell me this is the floor function. So we've got 8 graphs. Nothing too crazy, too in depth here, but I do want you to be able to recognize these going both ways. For this particular section on our drill, I will give you the graph and ask you to state the equation. But in the next section, you're going to need to be able to go in the opposite direction. Once you recognize the equation, be able to visualize what the graph is going to look like. So right now, even though you need to go in one direction, I would encourage you to be thinking about how these look in both directions, going from equation to graph and from graph to equation.